So in this video I'm going to go over the problems on version A of the quiz for sections 8.3 and 8.4. So I'll do every single problem sequentially, starting with number 1. So this is old version A. There's going to be a separate video for old version B problems. So number 1, you have 81 times m to the third power all underneath the square root. So my first step would be, when looking at a problem like this, is to separate the constant and the variables apart underneath their own roots, because the product property of radicals allows us to do this. Then I'm going to evaluate each of the radicals separately and see what I can do there. On the left we have an 81, which is a perfect square. Hopefully you recognize that. That was one of the easier perfect squares. So that is composed of 9 times a 9, or a 9 squared. Now, as we know, anything to the power of 2 can cancel its root. So all you're left with in the end is just a 9 from that first radical. The second radical, you have an m to the third power. Now we can break that down into an m squared times an m to the first power. This is the reverse to the product property of exponents. And again, something we can do, because m squared times m to the first power is m to the third power. What this allows us to do is isolate that m to the second power, because again, anything to the second power you can cancel out with its square root. Once we do this, we now have that m isolated. This m right here is only to the first power, so it's going to stay underneath the root. And it was a multiplication between everything. And now we're just going to write the problem as a whole. So it's going to be 9m root m. So that is the final solution to this problem. So again, break it up into constant and variables separately, then work on the constant, work on the variable, combine them at the end, and that's the answer. So that was 1. Number 2, is root 14x times square root of 2x. In a problem like this, you either look at the problem and try to see if you can simplify it, or you combine them right away. In this case, you have to combine it because there's really nothing to simplify. Here it's a 2x. Here it's a 14x. 14 is composed of 2 times 7, but both of those are not perfect squares, so nothing we can do there. So you're going to go ahead and combine these two problems under one radical. Again, the product property allows us to do this. Break apart and reform products of multiplication underneath one root, or break them into separate roots. Once I do this, I get 28 x squared. 14 times 2 is 28. X times x is x squared. Now I'm going to break them up separately into the constant and the variable. Again, the multiplication property, or the product property of radicals, allows me to do this. Again, the x's to the power of 2, I can cancel that with its root. So that is done. It's just an x. The 28, you can break it down into several things. 2 times 14. But the best way to break up 28 is probably going to be 4 times 7. Why 4 times 7? Because 4 is a perfect square. That's the biggest perfect square that is part of the 28. So we can break that down. It's the biggest factor that's a perfect square. So we break it down into 4 times 7. Then I'm going to further break this down into 2 squared, which is the 4, times the root 7. And the x just comes down. And then once again, cancel out the 2 to the second power with its root. Nothing I can do there. And of course the x is already all done. So now I just rewrite this problem. 2x root 7. And that is the answer to that problem. Combine, do your multiplication, break apart again. So you're essentially rearranging the problem in a way that's favorable for eliminating the square root using powers of 2 and perfect squares. So that was number 2. Let's do number 3 next. I'll go a little bit faster so that I can make this under 15 minutes. So if you have a fraction underneath the root, you're going to break it up into, into 2 separate radicals, because you can't have fractions underneath the square root or any root. On the top, you have a squared times a to the first. On the bottom, it's a perfect square. It's 11 squared. So I'm going to further break down the numerator into separate radicals. So hopefully you can see the a squared there. And now I want to eliminate anything that's the power of 2 with its square root. That stays. So as such, my final answer is a root a all over 11. That was a simple problem. Let's move on to 4, which is not quite so simple. Again, you have a fraction underneath the root, this time 4 over 7. And again, you're going to break it up into root 4 and root 7. The 4 is easy because that is essentially a 2 squared, and we can cancel out the power of 2 and the square root, which gives us 2 over root 7. Now we run into a problem. We have a radical in the denominator, which is a no-no for us, and it's a prime number. 7 is a prime number. There's nothing you can do to simplify that radical. So instead, we're going to modify this problem by multiplying it by a new fraction made entirely of root 7 over root 7. So it's made entirely of this. And the reason it's a numerator and a denominator, because all by itself, that's just the 1. So it doesn't change the original problem, because technically we're multiplying it by 1, but it allows us to rearrange it, modify it a little bit, in a way that's going to help us eliminate that bottom radical. So now we're going to multiply across. So on the top it's 2 root 7. So nothing you can do there, that's done. On the bottom, that's going to be 7 squared underneath the root. 7 times 7, 7 squared. And as we just know, we can cancel out a square root with its power of 2, which gives us a final answer of 2 root 7 over 7. I'm going to move on to number 5. So number 5, you had 4 values, and you had addition and subtraction dealing with radicals. In a case like this, you want to combine any of the roots or radicals that have the same root and radical. So you combine anything that has the same thing underneath the root or the radical. So you treat them like variables, and you combine things that have the same variable, like terms. So root 4, you can combine that. Root 11, you can combine those. So those two and those two go together. So 6 plus 2, that's 8 root 4. That's as easy as that. 7 minus 4, that's 3 root 11. And the only thing that's left here, this is a perfect square. So that's going to be 8 times 2 squared. This doesn't change. Then of course we can cancel out the power of 2 with the root. So that's going to be 8 times 2, which is 16 plus 3 root 11 as your final answer for number 5. Moving along to number 6, we have 2x to the negative third all over 3 to the negative second. So now we're done with roots. This is problems from section 8.3. And a problem like this, you want to flip or take the reciprocal of anything with a negative exponent in order to make it positive, because we can't leave a problem alone with just negative exponents. So this has a negative exponent. It's in a numerator. It's going to flip down and to the denominator. This problem has a negative exponent. It's going to flip up. Again, every time they flip, their exponents switch kind of polarity, so they go from negative to positive and vice versa. The 2 has a power of 1, a positive power. That 2 isn't going anywhere. It doesn't have to. So at the end, you're going to have the 2, which stayed, times the 3 to the now positive second power on the top, and the x to the now positive power to the 3 on the bottom. And then you simplify. 3 squared, that's 9. 2 times 9, that's 18. X to the third. And you are done with that problem. So 6 was super easy. Just don't make the mistake of dragging that 2 down with the x to the bottom, because that 2 is a separate base with a positive exponent, so it stays. Only the x to the negative third goes down. And the last problem, number 7. We have 4 to the negative 2 all over y to the negative 4 times x to the 0. Again, very similar to the last problem. I just threw in the x to the 0 to test you on the property of 0 for the exponents. So again, anything with a negative exponent will flip up or down depending on where it is. You take the reciprocal. So this base has a negative exponent. It's in a numerator. It's going to flip down. This base has a negative exponent. It's in a denominator. It's going to flip up. The 0 is not negative, so the 0. So it's just going to stay where it is. So that gives you, in the numerator, a y to the now positive fourth. And in the denominator, you get a 4 to now a positive 2. And an x to a 0. Next, you simplify. There's nothing to do with the y. That's just the y to the fourth power. That's going to stay. 4 to the second power, well, that's 16. Anything to the 0 power, so any exponent, so any base taken to the 0 power is 1. So that x to the 0 is just a 1. So the final answer is y to the fourth all over 16. So those were the problems on version A of the quiz for sections 8.3 and 8.4. I'm going to do a separate video now on version B, and that's going to be uploaded about the same time. So thank you for watching this, and good luck on the retake of the quiz.